Welcome to the Agrahood. Carnes Crossroads is a new home community with a farm-to-table lifestyle. Just outside of Charleston, here, community is defined by gathering together and our deep connection to nature.
Learn more at carnescrossroads.com.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again, and thank you for joining us on Space Nuts, where we talk about astronomy and space science and all sorts of other things. And it's great to have your company. My name is Andrew Dunkley, your host. And on today's edition, episode 290, by the way, we're going to do what we do traditionally every fifth episode, and that is dedicate the entire show to the audience. So these are questions that have come from you. Some we've heard from before, some we have heard from for the very first time. And not surprisingly, given that the James Webb Space Telescope has reached its destination, it has become the go-to topic when it comes to audience questions. So we're going to tackle a couple of questions about James Webb, but one of our old favourites is back, and that is the black hole. We'll talk about that as well. And look-back times. This is interesting. This sort of relates to the James Webb Space Telescope, but it's more specifically about how we sort of look into space and see what we're seeing, and plenty more, including questions about satellites in space and radiation shielding. That's all to come on this edition of Space Nuts. And joining me as always, my better half, my partner in crime, the man who knows all the answers to all the questions in the universe and beyond, Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. No pressure there, of course.
None at all.
She'll be right.
Always. Yeah, that's a great Australian attitude. She'll be right.
She'll be right.
Now, I know if you watch on YouTube, you can generally see where we are and what we're doing. Can you see what's over my shoulder, Fred?
Yes, I can. I can see a garment.
A garment, is that what you're calling it?
It's a garment.
That is something I've had for many, many years, a couple of decades. It is a Cincinnati Bengals jersey, and I've got it hanging up proudly because the Cincinnati Bengals are into the Super Bowl.
Okay.
So to our Cincinnati listeners, why not us? Why not us? Why not us? I'm very, very hopeful. Can't wait. I'll be stuck in an airport when the game's on, so hopefully they'll have it on there.
Yeah, hopefully, Andrew, hopefully.
Yes, I love American football. I understand the rules. I know how it all works. And I've been a follower of the Bengals, a long-suffering follower for nearly 40 years. So I've got my fingers and toes and everything crossed in anticipation.
Very
They're
good.
playing against the Rams, I think. I do like the Rams too. If Cincinnati hadn't made it, I would have gone for the Rams. So, but I'm not going to fall back on that. It's Cincinnati all the way for me. Okay, now enough of that. Nothing to do with space except the stuff between our ears. Let's get on to our very first question, Fred, and this one comes from Amsterdam.
Hi guys, this is Bart from Amsterdam, the Netherlands. I was wondering now with the James Webb Telescope in space and doing very well, luckily. And thinking about that it will maintain maybe for 20 years working. And it's taken a lot of time to develop this one. Are scientists already working on another telescope that even has more possibilities than the James Webb now? Okay, keep up the good work. Bye-bye from Amsterdam.
Thank you, Bart. Lovely to hear from you. Hope all is well in beautiful Amsterdam. And the James Webb Telescope is certainly getting a lot of attention, and not surprisingly, it's one of the most exciting projects of recent times. Are they working on something bigger and better, Fred?
Yes.
Okay, let's move on to our next question.
Okay. This is a multifaceted question, like they all are. It's fantastic to get questions that have got many different branches to the answer. And yes, the James Webb is it is the current front runner in terms of space observation, a 6.5 meter diameter mirror. Now, as you and I have spoken about many times, Andrew, in astronomical telescopes, size is everything. They don't miniaturize; they need to be big because the bigger the area of the whatever it is that's collecting the radiation, and for optical and visible light and infrared telescopes, it's a mirror. That the diameter of that means two things: you can collect more radiation, which means you can see fainter objects. But also, the laws of physics help you, because the bigger your mirror, the more detail you can see. It improves what we call the resolution in the image. So a 6.5 meter telescope is a huge step forward in space. I don't want, in any sense, to minimise the challenge and the triumph so far of the James Webb Space Telescope. It's an enormous instrument, 6.5 meter. It's actually very, very much among the bigger class of ground-based telescopes in the current era. So it will really revolutionize what we know about the universe on many, many different fronts. But astronomers, they suffer from an ailment which is called aperture fever. And it starts with amateur astronomers who buy a telescope, just like the one you've got, and you'll probably get it eventually, Andrew, where you think, yeah, this telescope's fantastic, but I just really need something a bit bigger, just to let me see that other moon of Jupiter that I can't spot or whatever. And that's the onset of aperture fever. Paracetamol helps to kind of cool things down, but really the only way to deal with it is to buy a telescope. So
I think I'm already suffering that, and I haven't really been into it that much yet.
Yeah. And so professional astronomers are the same, but it's a really interesting thing, because the James Webb is optimized for infrared radiation, and it's in space because it can look at wave bands in the infrared that are actually absorbed by the Earth's atmosphere. So that's, a great reason for putting it into space. Likewise with the Hubble telescope, when that was launched, it is a visible light or optical telescope, but with strong ultraviolet capability. It pushed our access to space radiation well into the ultraviolet, far more than we can see from Earth, because the Earth's atmosphere is really good at absorbing ultraviolet radiation, which is good because otherwise we'd all be burnt to a frazzle with sunburn. So the Hubble was sort of optimized for UV. Now, the Hubble's much smaller than the James Webb, but of course there's a quid pro quo here, because the resolution, the amount of detail you can see, is inversely proportional to the wavelength. You see more detail with smaller wavelengths, and ultraviolet is smaller. So the Hubble actually, in some ways, is comparable with the James Webb Space Telescope, even though the James Webb is much bigger, because it's infrared. It needs to be bigger to see similar detail. But of course, that the big plus is its size will let it gather more light. So to get to the question, there are things on the horizon, and I might just mention a couple. One is actually a project that is already, in fact already signed off on, and will launch no later than May 2027. It is called the Nancy Grace Roman Space Telescope, usually shortened as the Roman Telescope. Who was Nancy Grace Roman? She was one of the driving forces behind the Hubble telescope. So you can sort of see a link there. It's been named after her. Yep. But it is actually, it's an existing telescope mirror, 2.4 meters in diameter, the same size as Hubble. But the difference will be that it will be a wide field telescope. So unlike the Hubble, which homed in on tiny areas of space, this can do the same thing, but over much wider areas of space as well. And it will carry, once again, a near infrared camera, providing a sharpness of images really comparable to the Hubble, but over a much bigger field of view. So it's almost a successor to the Hubble. So in a sense, that doesn't rival the James Webb. It's not the next really big thing. there is in the US decadal plan for astronomy, the 2020 decadal plan, there is this is something the astronomical community puts together. It's the same thing happens here in Australia. They wanted a 6-meter optical telescope, an ultraviolet telescope, so something the equivalent of the Hubble, but with a 6-meter mirror, in other words, comparable in diameter with the James Webb. So that is likely to be the next big thing. And once again, it's all about looking at exoplanets and characterizing their atmospheres, which is one of the things that James Webb will do. So to come back to Bart's question, the answer is yes. But let me just add one more caveat. This is taking a long time. I'm sorry, Andrew. And that is that since the Hubble was launched, our technologies for minimizing the effects of the Earth's atmosphere have come along by leaps and bounds. And so you can now do Hubble-class detail imaging from the ground with some of the, the telescopes on La Palma and the Canary Islands, and Mauna Kea in Hawaii, down in Chile at Cerro Paranal. They have these adaptive optics systems, which means you can recover the detail in the image that the Earth's atmosphere blurs. And of course, the next generation of telescopes with their 20+ meter mirrors, they too will be equipped with this sort of kit, which means that in some ways they're going to outclass the space telescopes because they're much bigger. But what they can't do is look at radiation that is absorbed by the atmosphere. So mid-infrared radiation or ultraviolet radiation. They need space technology.
Will Hubble keep operating? They're not planning on decommissioning that, are they?
I think it's scheduled to operate for as long as its gyros last out. The problem with the Hubble is it is a large piece of space junk. It's a very heavy, a massive, orbiting body. So it needs to be, it's in a 600-kilometer orbit, but it does need to be deorbited. And I think the last mission, servicing mission, I hope I'm right in saying this, but it's, as I recall things, they attached mounting points onto the outside of the Hubble. This was the one before, I think it was before 2011 when the shuttle, wrapped up. They replaced gyros on the Hubble and also put these grapnel points on the outside, so a future robotic spacecraft can dock with it and deorbit it by using its thrusters to bring it down.
Okay.
Don't know when that'll be.
Very interesting.
Yeah. No plans at the moment, I think.
No. Well, just keep using it till it
till it dies. Yeah. It's still a fantastic resource for astronomy. Absolutely.
Yes, indeed. Good to know they're going to keep going that way as well, which, just expand our knowledge regardless of which method they use.
Exactly.
The technology is advancing so fast. Thank you, Bart, for your question. Let's move on to an old friend of ours, Paddy the Roofer.
G'day, Fred and Andrew. Paddy here, Roofer. My daughter Alyssa has got one more question about the James Webb. Now, it's 1 million kilometres away, and she says, well, how is it that far away? And if it's that far away, can it take a picture of Earth or where we live? I thought that was actually amazing what she said. But, can it take a picture of Earth? That'll look pretty awesome, I think, and that's what she reckons too. So may the force be with you, and that's it.
Uru. Thanks, Paddy. And Alyssa, nice to hear from you. And they sent a follow-up question. Well, actually, it was a preemptive question to that. We got two questions, one about taking photos of Earth from James Webb, but also, will it be able to take photos of exoplanets? That's something that we really should be considering. Will it be powerful enough to actually get an image of an exoplanet, good and proper? That's a good question. It's certainly going to be quite powerful. But let's go with the first part of the question, photos of Earth. Will it be able to do that? Is it going to be tasked to do that?
No, it won't. And the reason is, the reason why it's 1 million kilometres away I beg pardon, 1.5 kilometers, it's 1,000,000 miles, is to put it in orbit around this stable point, the L2 Lagrange point. And that point is directly opposite the sun from the Earth. So there's the sun, the Earth, and the L2 point, all in a straight line, with the James Webb in orbit around the L2 point. The reason why it's there is to give it a nice uniform thermal background. In other words, the heat of the sun on the spacecraft, it actually will fall on the radiation shield. That is to keep the spacecraft's temperature at, I don't know, it's about 20 degrees above absolute zero. It's very, very cold. So the last thing you want to do, and it would fry everything, it would fry the electronics and everything, is turn it round so that the heat shield is no longer protecting the telescope from the sun's radiation, and point it back towards the Earth with the sun nicely in the background there. It is not going to happen. And the telescope will always be looking in the other direction to keep it safe and out of the way. It's a nice idea, but it's the wrong telescope for doing that. It has to be kept absolutely cold.
What about photos of exoplanets?
It will do that, I'm sure. And there are already a handful of exoplanets that have been directly imaged. It's probably, I think it's less than 20, if I remember rightly, by telescopes equipped with devices that sort of block out the light of the parent star. So what you need is the adaptive optics systems we were just talking about, which get rid of the distorting effect of the Earth's atmosphere. And you need an instrument called a coronagraph, which is a device that it's basically just a mask in the focus of the telescope that blocks out the light of a star and lets you see what's around it. It lets you look at its environment in great detail. And there are just a few planetary systems that kind of lend itself to this sort of technology. Most of our exoplanets have been discovered by indirect methods. So it's quite rare to be able to see direct images of exoplanets. You can find them on the web. There's actually a movie of one of those systems where there are 4 planets doing this lovely resonant set of orbits.
I've seen that, I think. Yes.
It's fabulous stuff. But that's a rarity. But I think the hope of planetary scientists is that the James Webb will actually increase the number of targets where we can see the direct images of exoplanets.
All right. Thank you, Paddy. Thank you, Alyssa. And hopefully we answered your question. Just before we depart from the James Webb Space Telescope, the news this week, aside from its arrival at its destination, is that they have announced its first target, or one of its first targets, and that is a star in Ursa Major, in the constellation of the Great Bear, HD 84406, 241 light years away. They chose that one because A, you can't see it with the naked eye from Earth, but B, it seems to be an Earth-like sun, or a star similar to our own sun. So that's why it's interesting to us. So that appears to be the first target for it.
Yep. And we wait the images of that with interest.
Yes, it's going to be a few months yet, isn't it?
It is, yeah. Really, it's a few months. That's
mid-year, probably, before they start sending us piggies on Instagram, I believe. All right, we'll continue shortly. You're listening to Space Nuts with Andrew Dunkley and Fred Watson.
0G, and I feel fine.
Space Nuts.
I'd just like to send a little shout out to our patrons, the people who choose off their own bat to support us financially. We really are appreciative of that, and there are several people that do that. They're in the hundreds now, so that is fantastic. If you would like to look into becoming a patron, you can do that via our website, spacenutspodcast.com, and just click on the supporter tab and find out more about it. We're not going to make you do it. We're never going to make the departing of money from you to us a mandatory part of the deal. it is certainly optional, but for those who have certainly decided to do that, and it was a listener idea at the very beginning, thank you, and it is greatly appreciated. Now let's continue with the questions, Fred, and our next one comes from, I think it's New York.
Hi, Andrew and Fred. I have a question relating to the James Webb Telescope. This is Richard from New York, and I love your show. I have questions about the plan to peer into the deep past to see the stars and galaxies from the first billion years after the Big Bang. What I do not understand is how one can do that. Now, I understand that distant objects whose light is very much red-shifted are furthest away and receding from us the fastest, and that they are presumably older because the light they emitted and that we see traveled so long to get to us. But it seems to me that any object that emitted light during the first billion years was necessarily a lot closer to our vantage point, the universe having been smaller then, and that light emitted must have passed us in space long ago. So how can we ever see it? Now, if we are carried by expanding space away from that light source faster than the speed of light, then the light will not reach us at all, or will be visible behind us as we catch up to it. If the light is riding on expanding space along with us and always traveling at the relative speed of light like it's supposed to, then that early light should still have passed us by. We cannot see yesterday's light. Once I was told that the telescope can be aimed in every direction to see the beginning of the universe because there is no center point of origin. Space expanded everywhere, so everywhere is the same. Nevertheless, everywhere will have emitted its early light so long ago that it still must have passed us here long ago. So where am I going wrong? Look forward to your answer. Thanks a lot.
Actually, Richard, while you were going through your question, I was watching Fred and he was nodding and shaking his head. So I think what happened there is you were hitting a nail and you hit it a few times and you missed it a few times. So, yeah, okay. Richard did ask where he went wrong. So, yeah, where do you want to start?
Well, let's start at the beginning. The bit that Richard was saying about the universe being effectively the same in all directions is correct. And yes, we can look back to still see the flash of the Big Bang, which is the most distant and most ancient thing we can see. So the first thing is to forget all about light going past you. Just don't think of that, because that's not the way to visualize it. What you have to visualize is us here on planet Earth in the solar system, attached to the Orion Spur near the Sagittarius arm in the galaxy. There you are. That's the full address. That's our vantage point, and everything. All we can see is stuff that's coming towards us. Now, there's light going in all directions, all around the universe, going past us, doing all the rest of it. But none of that is of any importance to us. The only thing that's important is what comes to us here on Earth. And that sort of makes it easy, really, because it means that we are effectively at the center of this bubble of space with light coming towards us. The only light that we can detect is what's coming in our direction. Mm. And yes, it has the attributes that Richard has mentioned. First thing to do is to forget about the expansion. Just imagine that the universe is not expanding. It's a reasonable assumption to make, because it's a separate issue from the look back time issue. Okay, so you've got this universe, this huge volume of space, and the light moving around in it is traveling at 300,000 kilometers per second, the speed of light in a vacuum. And that's why when we look further and further into space, we're always looking further and further back in time. And it, the idea of light going past us is irrelevant. All that's relevant is what we receive on Earth. and it's got this exact relationship. You look out in space a million light years, you're looking back in time by a million years. You do it for 10 billion light years, you're looking back in time 10 billion years. And for that reason, we often call it the look back time. And the look back time is actually more factually correct than a distance. And that's because, as Richard says, the universe is expanding. So a look back time is really what we measure when we measure the redshift, not so much the distance. We're measuring the look back time. In fact, the actual mathematical relationship is a really easy one, believe it or not. And it's a geometrical one. So what you can do is the redshift is a quantity that we call Z, or I guess Richard would call it Z, because that's how it's pronounced on that side of the Pacific. Z is measurable. Geometry tells you that the relationship between the size of the universe now and the size of the universe when that stuff was emitted, when that light was emitted, is a very simple formula. It's 1 over 1 plus Z. So what it means is if you're looking at an object with a redshift of 1, that light was emitted when the universe was 1 over 1 plus 1, in other words, a half its present size. And that is pure geometry. That's nothing to do with theoretical modeling. That's pure geometry. Maybe I've clouded the issue a little bit there, but the expanding universe is, if you like, it's superimposed on the idea of look-back time. The reason we don't talk about distances is because, yes, the universe has expanded, and as Richard has said, those very distant galaxies were much closer to us when their light was emitted. But they're still emitting light, and we're still seeing it. Some of it, don't worry about them going past us. It's what we can see now that's the critical thing. I don't know, Andrew, whether that clarifies the issue or not.
I get it. I get it, and I'm sure Richard, who is much more astute than I, has gone, okay, now I understand.
Let me just add one more point. So the idea of seeing the birth of the universe, it's actually looking back to a time when the universe was still glowing brightly. So it was still a fireball. And yes, we can look back by this method that I said. The further you look, the more you're looking back. Eventually, you reach this wall of radiation, about 13.8 billion years look back time. That wall of radiation, if the universe wasn't expanding, it would still be there. It would still we'd still look back to this, but the whole sky would be brilliantly light. It would be just the sky itself would be glowing brilliantly in visible light. But because the expansion of the universe has taken place over 13.8 billion years, that light's wavelength has been stretched, and it's now microwaves, which is why we see it with microwave telescopes.
Okay. So just to confuse us more, you've got distances measured in light years. You've got look-back time, which tells you how long ago
the light was
something
emitted.
happened.
Yep.
And there was something else that I just dropped out of my head.
The redshift
relates to it. But there are multiple factors here that you need to consider depending on circumstance.
But the main thing is just to forget light that's not coming into our telescopes. All we can do is, all we can see and all we can learn from is the light that actually reaches us from these distant things.
Fair enough. All right. Thank you, Richard. Let's go on to our next question. This one comes from an Australian.
Damien here from the Goldie. Another beautiful day. And a quick question on black holes, amazingly. If you have the size of the black hole and you have the mass of the black hole, if you had protons cheek to cheek inside the black hole, would they fit in there to equal the mass of the actual black hole?
Okay, thanks, Damien, and I hope all is well on, he called it the Goldie. For those who went, where the hell is that? The Gold Coast in Queensland, Australia. We abbreviate everything over here, so Goldie. Yes, explain his question, Fred, so that I can understand it, and that way everyone should be able to.
Yeah, well, it's Damien's question is really interesting because it's sort of it's got a few inconsistencies in it, if I may put it that way. Let me start by talking about it. Damien talks about the size of the black hole and the mass. And a black hole doesn't have size. It is a single point. It's a dimensionless entity. It does have mass, however.
I did see a diagram that somebody put up. It might have been on one of the Space Nuts Facebook pages the other day, which was a simple diagram of a black hole. And it basically sort of went wide, then narrowed down into a flute, and then hit a point that was nothing, called a singularity.
Yeah.
And then it expanded out the other side the same way. So
that sounds like
that's what you're getting at.
Sounds like a wormhole there. Could be a wormhole.
Well,
yeah.
If it was supposed to be a diagram of a black hole.
Okay. Anyway, whatever it is, it's got no dimensions. What does have dimensions, though, is the event horizon. And so, the event horizon is the point of no return. It's the black bit of the black hole. But the diameter of the event horizon is directly related to the mass of the black hole. So the two of them are, they're inextricably linked together. Now, the bit about if you had a bunch of protons all cheek to cheek, then it wouldn't be a black hole. It would be it would be a neutron star. Neutron stars are made mostly of neutrons, but they do have protons as well, because otherwise they wouldn't be able to have magnetic fields. And that object is something whose density has not become enough for it to collapse into a black hole. So it's the result of the core of a collapsed star. I do get what Damien's saying, though. Would a neutron star fill the event horizon of the equivalent black hole? And the answer, as I remember rightly, neutron stars do have event horizons because they're actually very dense objects, but I think the event horizons are actually inside the neutron star. I'd have to check up on that. That's something that's come from somewhere in my brain. Neutron stars do have physical dimensions, black holes don't. That's the big difference between them.
Of course. All right. Thank you, Damien. Hope that helped. Ibuprofen would help too, as Fred alluded to earlier.
Yes.
This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Space Nuts.
Now, if you follow social media, of course, you will find us in many, many places. We're on Twitter, we're on Facebook, we're on Instagram. And we also have a Facebook page, which is basically designed for the Space Nuts audience, the Space Nuts podcast group. If you do a search for that in your Facebook search engine, you'll find a bunch of people, thousands of people who listen to the show, but also get a chance to talk to each other. One of the posts, Fred, that's popped up lately comes from one of our patrons and somebody who does send us questions occasionally, Misty West, who's put up photos of what looks like a spiral galaxy in the sky over Oklahoma. And she's asking if anyone had seen it and what was it. And one of the answers said it was an orbital insertion burn, which probably is a pretty accurate appraisal of what the picture is, but is spectacular. The photos are spectacular. So go and have a look at them on the Space Nuts Podcast Group Facebook page. Really stunning pictures and quite pretty as well. And while you're there, join the group and talk to like-minded people about astronomy and space science. That's what it's all about. You don't just have to listen to us. You don't have to listen to us, but you can certainly sort of expand the conversation by being a part of the group. And while you're on Facebook, join the official Space Nuts Facebook page while you're there. Okie dokie, Fred. Let's see what else we can solve today for Simon in Melbourne.
Good evening. It's Simon here from Melbourne in Australia, enjoying a nice weekend way down at Barwon Heads. Looking up into the night sky, I've managed to identify Sirius and Conopus this evening, which is the first time I've been able to locate both of those two by myself, so it's quite exciting. Lots of people have been telling me to bring down a pair of binoculars, and I've done just that this evening, and I'm absolutely amazed at how many satellites are up there. At one point this evening, I noticed 3 satellites converging on the one field of view, and I just can't believe how much stuff's going on up there. As sure as the night is dark, you will see a satellite if you throw a pair of binoculars up into the night sky. From my perspective, it doesn't bother me too much. It's more exciting to identify them. But if you're an astrophotographer or an astronomer, I can imagine it being very frustrating. So my question to Fred is, what do you propose doing about this? I understand regulations probably needed, but how would you like to see this organised or structured? And how do we go about protecting this sky for future people? Because I can understand it becoming very frustrating moving forward. So I'd like to understand, what are we going to do about it? I hope all is well, and thanks for keeping up the good work, guys.
Thank you, Simon. Great question. And I can tell you that Fred is in negotiation with Disney to commission an X-Wing fighter to get up there and deal with the satellite problem. Possibly not.
You're treading on not on eggshells, but on interesting ground, Andrew. And look, the short answer to Simon's point is welcome to the 21st century, because this is an issue now, but by the end of the decade, it is going to be a much, much bigger issue. We are expecting, at the moment, there are something like 2,500 operational satellites in the sky. By the end of the decade, it'll be 100,000.
What?
Which means that at any instant, there will be about 5,000 satellites above your horizon. Now, that's because of things like the SpaceX Starlink satellite constellations. Those are they're for global internet. They provide internet services across the entire globe, and there's a level at which that is a good thing and part of the sort of infrastructure that perhaps people have a right to expect. And so there is this really interesting. It's a dichotomy. It's very interesting. I'm quite deeply involved with it, between the space industry and the world of astronomy. And the good news is that these two different entities are talking to each other about how you mitigate the damaging effects of satellites on telescopes. And of course, it's not just astrophotographers in the hobby category. It is the world's great observatories, including things like, not so much the James Webb, although the Hubble telescope loses about 8%, I think, of its observations because of interference from other spacecraft.
That's a lot, Fred.
It is, exactly, yeah. So there's, there's this relationship between the satellite operators and the astronomical world. I have to say, the world of astronomy was taken a bit off guard by this. It's about 3 years ago now. What has prompted it, to some extent, is something that we all applaud, and that is the reuse of rocket boosters by SpaceX. The fact that, Musk's brilliance in terms of developing the reusable rocket booster means you can use the same booster to launch 10 lots of satellites. You can use it 10 times. Starlink launches about 60 from one launch vehicle. So it means you've now got the wherewithal to have these large numbers of spacecraft in orbit. The regulatory body for this it's a bit esoteric, because the regulatory body is there not to regulate how many spacecraft there are in the sky. It's just to regulate the spectrum management of the radio signals that those spacecraft provide. It's the International Telecommunications Union. That's the global body. Each country then has its own agencies that do the regulation. Like here in Australia, we have the Australian Space Agency that does regulation on that. So there's the industry ploughing ahead on one side, and the astronomers there were certainly howls of pain at the beginning, but there is a dialogue now that is moving towards, I think, some really good measures to mitigate the effects. So the kind of thing you've got to remember is for visual astronomers or optical astronomers, these satellites are only a problem. It depends on your latitude, but they're only a problem within an hour or two of sunset or sunrise, because that's the time when they're being illuminated by the sun. And that's the reason why one of the things that the astronomers have asked for is that the spacecraft are kept in low Earth orbits, that's to say below 600 kilometers, because that reduces the time that they're illuminated by sunlight. And that's one of the things that this dialogue is engaging in. So in the middle of the night, there is no problem. You don't see, there are some slightly maybe esoteric problems if you have a satellite that blocks out the light of an object that you're expecting to be winking anyway for some reason or another. That will be a problem. But generally speaking, once you get past the twilight zone, you're not actually seeing the spacecraft. However, in the radio spectrum, it's a much bigger problem because these things are beaming down radiation all the time. And not just that, but for our telescopes, the most sensitive radio telescopes, and of course the square kilometre array being built in South Africa and in Western Australia is one of those. They can also receive radiation from local radio transmitters providing AM signals to their community. They can bounce back off the satellites down into the radio telescopes. So there are big issues for radio astronomers. As I said, it's a matter under discussion. In a few days' time, there will be the start of a meeting in Vienna. That is a UN meeting. It's the UN Committee on the Peaceful Uses of Outer Space. And they will include among their discussions
disconnected or
this discussion of what is generally lumped under the heading of dark and quiet.
I don't know what's happened there.
Dark for optical astronomers, quiet for radio astronomers. In fact, I'm going to be part of the Australian delegation on that. I think it's a secret to say that, and we'll be presenting a technical paper on this. But it's a interesting area. It's not just something, Simon's question was, what can we do about it? Well, we're doing our very best to bring these two disparate fields of activity together to make them compatible.
There you go, Simon. Hopefully that resolves your problem, or you didn't actually have a problem with satellites, but you might in a few years with 100,000 of them expected to be up there. But anyway, thanks for your question. Good to know, Fred, that the two sides are talking, hopefully not the way Russia and the United States, or the Russians and the Americans and the Chinese are talking, or Australia and France for that matter. Hopefully it's more like a couple of blokes over a beer or having a cup of coffee together, and they'll sort it all out in the end. Fingers crossed. Okay, let us move on to our final question. And this one focuses on long-haul space travels. It's something we've talked about before, but it's a good question.
Hello, Space Nuts. Martin Berman Gorvine here, writer extraordinaire in many genres. Just a quick question about radiation shielding on spacecraft that are going to go much beyond low Earth orbit. We are told this is going to be a major problem for any proposed Mars expeditions. One assumes it would be an even greater problem going further out, say if one were going to try to do manned mining of the asteroid belt, or explore the Jovian and Sertanian moons and so forth. What kind of radiation shielding to preserve human life might be possible on spacecraft? And is it conceivable that instead it just makes more sense to send automated probes to do all that stuff for us? Thanks. Love you guys.
Thanks, Martin. Lovely to hear from you again. It is a big issue for future travel, especially as Martin mentioned, sending humans to Mars. But I think ultimately we might be looking at going even further when we improve speed and technology that will enable us to do those trips in reasonable timeframes. But at this point in time, exposure to radiation is one of the problems, but the health implications of zero G also have to be considered. So they're probably working on artificial gravity as a part of this whole picture. So, what are they working on in terms of radiation shielding?
Thanks, Andrew. Yeah, it's a great question from Martin, and I mean, what Martin says at the end is really the key to it. Send robots, and we can do that for a lot of the tasks that we would like to accomplish in exploring the outer solar system, or the inner solar system as well, for that matter. And I suspect if ever we do get to a stage where we're mining asteroids or other celestial bodies, that it will be done mostly robotically, with as little human intervention as possible. Partly because this is recognized as such a big problem. The radiation environment in space is pretty harsh, and you're right to highlight the more extreme version of the radiation environment that we would get in going beyond Mars. Mars is really the first hurdle, and there's a lot of work being done on that. You can bet your life on that, and I'm pointing to some of it in a minute. But if you're going beyond Mars, heading to the asteroid belt or out towards the moons of Jupiter, first of all, you've got the bad thing, which is that you're going to be in space for much longer, because these distances don't just increase linearly. The distances, as planets go further out, they get more and more remote. So you're talking about much greater distances if you're heading for the asteroid belt of Jupiter. Against that, though, is the advantage that the radiation environment gets a bit easier, because you're further away from the sun, which is the principal source of this radiation. So there's a bit of interplay on both sides, quid pro quo. However, the basic problem is not a straightforward one, and I'd actually point Martin towards a really excellent publication from NASA, which will be easy to find. It's part of the spacefaring series of NASA documents, and it's called the Radiation Challenge. Oh. Radiation Challenge. There is one. I think this is one module of that course, if you can put it that way. Module 3 is radiation countermeasures. How do you protect against radiation? And there is a lot in this particular document. The spacefaring Radiation Challenge document. Really a lot of food for thought, because the problem is not as simple as you might think. Our natural thinking in terms of protection from radiation is sheets of lead and things of that sort, which is not really that friendly towards being hauled up on a spacecraft.
Water too, wasn't someone talking about?
Yes, water is another possibility, and I think it's water that is likely to be the most commonly used. But some of these materials, you get hit by a cosmic ray, and actually the cosmic ray environment doesn't change throughout the solar system, because the cosmic rays are coming from way beyond the solar system. So, and they're higher energy actually than the sun's radiation. So this is all part of the complexity of the issue. So you might well get, for cosmic rays, they'll hit something in your shielding, and you get a whole cascade of secondary particles being given off, which are just as dangerous as the cosmic ray itself. So really, there is a lot of thought and insight that has to go into this. I know that NASA have been investigating, electrostatic shielding, where you try and generate an electrical field around your spacecraft so that the radiation gets bent away from the spacecraft. And plastic shielding is another possibility as well. But there are countermeasures, perhaps indirect countermeasures, which might be a bit surprising, Andrew. Dietary countermeasures, for example. Operational countermeasures they're talking about. There's a whole lot of material on dietary countermeasures. I would have thought
eating lead would not be a good thing.
It's that sort of thing. It's actually what you don't eat. I think that is the that's the trick to this.
Well,
to talk about.
Don't take any antibiotics while you're out there either. They can cause sunburn.
Well, the kinds of things. Okay, here's something in this module: shielding yeast from ultraviolet radiation. It's an exercise within this module of education about how you can you can take radiation countermeasures. So I urge anybody interested in this to have a look at that. It's really it's part of the some of NASA's national education modules, but really very, very interesting in terms of what you learn from something like that.
I did, in fact, try to contribute to that module, Fred, but they didn't think aluminium hats was a real good idea.
Sounds like a very Aussie solution, does that? You've got to twist them at the top as well.
Yeah, a little pointy bit. Yes, I think that's been portrayed in many films. So they're working on it, I think, is the answer, Martin.
That's the bottom line. They're working on it. Yeah.
No solutions yet, but some pretty good ideas. And again, lovely to hear from you. Thanks to everybody who contributed to this week's episode. All questions. It only took us 6 or 7 hours to put the show together in about 25 takes, didn't it, Fred?
It was not the easiest recording of Space Nuts that we've done, Andrew, but it sounds as though we're getting there, thanks to your sterling efforts and probably some of Hugh's as well later on.
I would equate it to the most difficult one we've had so far, but if I can solve it, NASA's going to do some great things into the future.
Yeah.
If I'd put my aluminium hat on earlier, we would have finished this morning.
So you're blaming the radiation.
That's right. It's all about the radiation, yes.
Yeah.
Okay. Thanks to everybody again for sending in your questions. We'll get a pile more done as we move over the next series of episodes. Don't forget to, through your regular podcast platform, to give us a review. We've been getting some great reviews, and thank you so much to those who have put up reviews. Lots of 5-star ratings, a couple of 4.5 stars because they don't like my jokes. Well, you know what? They're not going to stop. But thanks for the reviews. It's really fantastic. And while you're online, please visit our website, check out the shop. You can send your questions through our website as well in text and audio form. And you can do a lot of other things there as well while you're browsing around spacenutspodcast.com or spacenuts.io. That finally brings us to the end of this week's episode. Fred, thank you so much.
It's a pleasure, Andrew. Thank you for persevering, and we'll speak again soon.
We will. And if people have noticed through the high-definition picture that I've got a bit more stubble than I had in the first 2 segments, it's the time difference that's caused that. At least we continued to wear the same clothing. It's just like making movies. Anyway, thanks for your company again, and we look forward to you joining us on the very next episode of Space Nuts. Until then, bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.